Hello, everybody. Welcome to this session devoted to discuss about why and how the sun and the stars shine and the Borexino experiment. This is the second block of this special session. We had one yesterday and there will be another one tomorrow. We have detected all the neutrinos coming from the sun with the Borexino experiment. And this meeting, these sessions are an important opportunity to review the performances of the Borexino experiments, the results, and their interpretation in the context of solar physics. So we start today with a presentation by Alessio Caminata about the performances of the Borexino detection. Alessio, I think you can share screen and start your presentation. I will alert 5 minutes before the end.
Perfect. Thank you, everybody, and thanks to the organizers for allowing me to present this nice work to the conference. I hope you can see my slide. So, since this is the first talk about Borexino in this section, I will also review a bit not only the detector performances, but also how this detector is built and which were the ideas behind the choices that were done. So Borexino had the main goal to detect low energy solar neutrinos, in particular beryllium-7 neutrinos. It's a detector currently taking data at the Laboratori Nazionali del Gran Sasso, so in the central part of Italy. And it takes data since 2007. So it's quite a long time. And the chosen detection method is look for the Laxer scattering of neutrinos on electrons. So as it is written here, we are sensitive to all the flavors of neutrinos with different sensitivities, but we can basically detect all the neutrinos. So electron, muon, and tau. So the medium is a large mass of organic liquid scintillator, so a material where if energy is released on it, we can detect the interaction because the material emits light that is proportional to the energy released on it. So the biggest problem here is the cross-section. Since we are talking about neutrinos of the order of 1 MeV or less in energy, we have really low cross-sections. And in 100 tons of the Borexino liquid scintillator, we expect of the order of 50 counts per day for beryllium-7 neutrinos, which corresponds to 10 to the minus becquerel per kilogram. This value is really low. It means, just for comparison, if we look at natural water, we have of the order of 1 becquerel per kilogram in uranium, thorium, and potassium. So if we want to have a high signal to noise level, we need to have a huge effort to achieve extremely high radio purity levels. So this is the main difficulty that Borexino had to face at the design and construction level. So let's review how we can build a rare event search experiment. So we have to take in place some mitigation strategy for the background. And so we have to reduce the external background, so the background coming from the environment where the experiment is, and also the internal background, so the background coming from the construction materials, for instance. So for the first, external background, if we want to reduce the background, we need to go underground to reduce the contribution of muons, so cosmic rays, and also to add passive shielding to, let's say, insulate from the environment of the lab. But it's not sufficient. We need also to reduce the internal background. It means that we have to carefully screen and select the materials with low radioactivity levels, we need to reduce the mass close to the scintillator, so close to our active volume. And okay, since we are talking about liquid, we can also perform purification of the scintillator. Just keep in mind that this strategy is almost the same for all low statistics experiment looking for rare events, basically. So just a word about where we are. We are at the Laboratorio Nazionale del Gran Sasso, so in the central part of Italy. Its altitude is 963 meters, and it's an underground lab, so we have an average rock cover of about 1,400 meters. And this is equivalent to 308,000 water equivalent meters of shielding. And this means that the muon flux is reduced by a factor 10 to the 6 with respect to the surface. So we expect something like 1 muon per square meter per hour. And in this chart, you can see where is Laboratorio Nazionale del Gran Sasso and the muon flux with respect to the other labs in the world. So after having looked at the strategy to mitigate the background, let's see how the experiment was built. So the core is here in the center, 280 tons of liquid scintillator. It's made of pseudocumene plus PPO, and it is contained in a 125 micrometers thick nylon vessel that separates the active volume from two buffers of non-scintillating material, that is a quenched scintillator, with a total mass of 900 tons. This buffer insulates from the radioactivity, gammas, basically, coming from the construction material that are a stainless steel sphere and 2212 photomultipliers. These photomultipliers are the transductors that are used to look for scintillation light. All this stuff is contained in a water Cherenkov tank, 2.8 kiloton of ultra pure water that has the role of a shield from gammas and neutrons from the environment, and also an active veto for muons due to the Cherenkov effect. And for this purpose, we installed in this water Cherenkov tank 208 pin tips. And here you can have an idea of the size of this detector. Let's just say that the radius of this vessel is 4.25 meters. Here is a slide with a couple of pictures. The first one here is taken from a camera installed in the sphere, where, let's say, in a place of a photomultiplier. And you can see in the background all the photomultipliers with a cone that helps maximizing the light collection. You can see the vessel containing the scintillator. And while on the right, you can see the external of the tank, of the water Cherenkov tank, with a thermal insulation on it. In this slide, I show you just a list of contaminants and also which are the mitigation strategy that we adopted for reducing that amount or that contribution. So I will not go through all of them, but just from few examples. The first one are the muons, and the strategy to mitigate the background is to go underground and use a water Cherenkov tank. It's nice to see the effect of carbon-14, because typical amount is 10 to the minus 12 gram per gram, but the requirement for the experiment is the order of 10 to the minus 18 gram per gram of carbon-14. And so we were able to achieve this, to achieve 2 times minus 10 to the minus 18 gram per gram, just selecting the sources and the vendor of the pseudocumene, where the oil from which it was made was from really deep wells. Another example is Crypto-95, that is normally in the air and a product of a nuclear reaction. And to have a really low amount, we had nitrogen stripping on the scintillator itself, and also not exposing the materials to air. So the core of the experiment, so what we really need to then deliver physics is to understand this scintillation light, because from it and from its detection by 2212 photomultipliers, we can get a lot of information. We can get the particle identification, looking at the light versus time. We can reconstruct the energy of the event, so from the total light collected by the PMTs. And also we can exploit algorithms to get the position of the event, basically using algorithm of time of flight. Unfortunately, scintillation light is isotropic because it comes from the excitement of molecules, so there is no directionality. And since this talk is more focused on the detector performances, the performances are that the error, so the uncertainty on the energy, is the order of 50 keV at 1 MeV, so 5%, and the uncertainty on the position is 10 centimeter at 1 MeV. Here you can see just a picture of a photomultiplier. Here is the emission spectrum of the PPO, so what really emits the scintillation light. And here is the quantum efficiency curve for the PMT. So when I talk about particle identification, we can see here from this example that an alpha and beta have really a different distribution of light versus time. You can see that the alpha signal is longer. And so exploiting this different amount of light versus time, we can develop algorithm to distinguish alpha and beta. This is okay. We have different algorithms. All of them are described in our paper, in this paper, and also in a previous one, more on solar physics. And here is an example of a multi-layer perceptor that we developed, and it was used for example, geoneutrino measurement, and a more rough version also in the paper about the modulation of the Billion 7 signal. But you can see the high rejection power that we can get for alphas if we are looking for beta, in this example for the polonium 214, bismuth 214 decays. We can not only disentangle alpha and beta, but we can also have some power to distinguish between E plus and E minus, looking at a likelihood for the position reconstruction, because electrons deliver point-like energy, basically, while for positron, after the positron releases its energy, it annihilates, emitting two gammas, and consequently, we have, if you look at the likelihood function for position reconstruction, we have a broader distribution. So we have some rejection power for E+. This is an example for a carbon-11 sample. And you will see in next talks that this is really useful for the solar analysis. Okay, so how we test the performances? To test them, we performed some calibration campaigns with different aims. They were performed between 2008 and 2010. And we deployed different sources inside the scintillator. To do this, we have a system with an arm where we can attach a vial with a source at the bottom, and also a light emitting source that can be pointed by the cameras. In this way, we know exactly where the source was positioned. And then with an hinge, we can map basically all this position within the vessel. So here is an example of a vial for alpha beta sources, but we perform also calibration with an aberration beryllium source to look at neutrons signal. And also we had an external calibration system where we can put a thorium source nearby the sphere. And this is really important to help us understanding the external background, so background coming from the sphere and also from outside the scintillator itself.
So you have 7 minutes. Perfect.
So here is a list of all the sources that we used: gammas for energy reconstruction, alphas from radon and polonium, so for position reconstruction, ammunition beryllium for neutrons, and then we perform also some calibration with light. We have different energy estimation, estimator, the number of PMT hit, the hit on all the PMTs, and the total charge. You can see that charge is more linear, while these three estimators are mostly equivalent at a low energy. We have position reconstruction capability exploiting time of flight, as I said, corrected by the shape of the signal that changes with the number of photoelectrons that are detected. And here you can see our resolution as a function of the total charge. Of course, the higher the light, the better is the resolution. And this is the comparison between done with calibration sources for position reconstruction, looking at the position of the source known by the optical system, and with the reconstruction, we have a slight bias in Z at a level of 4 centimeters. This is taken into account at an analysis level, and it impacts less than 0.2% at the level of fiducial volume reconstruction. Another thing that we need to understand the performances is the vessel shape, because we have a small leak in the vessel, so its shape changes with time. And so basically what we do is look at the events of bismuth, potassium, and thallium on the vessel itself, so in this energy range. And in this way, looking at how these events evolve with time, we can reconstruct the vessel shape. The precision is the order of 1%, or let's say more plus or minus 5 centimeters. And this is done on 3 weeks basis. And then with the laser source, making different runs with different laser intensity, we were also able to test the trigger efficiency, and also we cross-checked it with SR85 sources. And for the energy range for the analysis, the trigger efficiency is compatible with 100%, because we have choose a hardware threshold of the order of 50-60 keV, so well below our analysis threshold. So last thing I want to show you in this performance review is our approach towards analysis. And so we had 2 models, a Monte Carlo one and an analytical model. The Monte Carlo one is based on GEM4 and for the physics, and then a custom C++ simulation for the simulation of the electronics. And the performances are then checked with calibration campaign. So basically, here is the way we tuned our code, so starting from materials and study of light collection, absorption lengths, then focusing on scintillation times and energy scale for betas and alphas, and then simulating the electronics parameters. Here, the take-home message is that our code is in agreement within 1% in the solar analysis fiducial volume tested with the polonium-210 events, and the discrepancy is anyway lower than 10%, or 2% in the whole fiducial volume. Within all the scintillator that is used for instance, the Neutrino analysis. And we are able also to reproduce with this Monte Carlo the feature of the external background. So here is an example with the sources in the center for our calibration source, blue Monte Carlo, black data. Here is the discrepancy from the center of the detector for what concerns the solar fiducial volume. And here is the discrepancy with respect to the vessel. So you can see that the biggest spread is really close to the vessel, while then stays well within 1%. Here is an example of external background, where you can see that we were able to reproduce the shape with the Monte Carlo, and also to reproduce the ratio between the full absorption peak and the Compton tail, with different source position that takes also into account, consequently, the difference on the vessel shape. And here is a check for position reconstruction. My last word is for the other model that is analytical. In this case, we want to produce analytical PDF to reproduce the energy distribution of events. I will not go, of course, on all the details. You can see all the details here in this reference. But here we take into account, for example, the Cherenkov effect, the not uniformity of light collection. We take into account that the Cherenkov effect as a threshold, and also the triggering and the quantum efficiencies. So it's a pretty elaborate model that works really well. So we have two independent models that can be used to cross-check our analysis, and this gives us a lot of robustness. So in conclusion, Borexino is a liquid scintillator detector tailored for solar neutrinos detection, but as you can see now in the next talks, it has delivered more physics than only solar neutrino detection. The performances are the energy resolution of the order of 5% at 1 MeV, and the position resolution of the order of 10 centimeter at 1 MeV. And we have models that have agreement with data at the order of 1%. And so these performances allow Borexino to deliver important results in neutrino and solar physics, and that's it. So thank you for your attention.
Thanks a lot, Alessio, for your nice review. And we have time for just one question, if someone is willing to ask. So I do not see raised hands. And so in this case, we thank Alessio again, and we invite the next speaker, which is Daniele Guffanti.
Thank you. Bye.
Daniele will talk about the measurement of the PP chain solar neutrinos in Borexino.
Hello. So I'm sharing now my screen. Okay, can you see the slides?
Yes.
Okay, excellent. So now I will talk about one of the main scientific accomplishments of Boraxino, and that is the investigation of neutrinos produced throughout the entire PP chain. So the sun, as most of other stars for most of their lifetime, is fueled by nuclear reactions taking place in its core. And this core of the sun is usually inaccessible to conventional studies that we perform using the optical spectrum. But thanks to the tiny cross-section of neutrinos, as Alessio mentioned before, which makes their detection so challenging, in this case, there's also a blessing, because neutrinos are copiously produced in the core, and the sun produces more than 10 to 38 neutrinos every second, and these neutrinos can cross the entire profile of the star, reaching our detector basically almost unaffected. So neutrinos are basically the only direct probe to the sun core and to the nuclear processes that power up a star. So what is this? What are the processes then? Now, the main process fueling a star is the fusion of protons into helium nuclei. This process can happen through two different mechanisms. The first is the so-called PP chain that you see here on the left. That is a chain of nuclear reactions starting typically with the fusion of two protons into a deuteron. We see that this deuteron is then forms then helium-3 and then combined creates helium nuclei. Most of the cases, this chain can have different branches, and the main one here we see that terminates without producing neutrinos, but in other branches, other neutrinos than the one produced in the first fusion of protons are also released. And we can measure basically all of these neutrinos with Borexino. The other mechanism that can fuse protons into helium is the so-called Cno cycle. In this case, it's not a chain of reaction, rather a cycle that is very much subdominant in the sun, accounting for only 1% of the total luminosity. Here, the fusion is catalyzed by the presence of carbon, nitrogen, and oxygen. But as I said, this is subdominant, and although it's very interesting, this will be covered in other talks during the session. So I suggest you to stay connected for this talk to hear more. Now, given these two processes, we can try to understand how our sun looks like through the so-called standard solar model. The standard solar model, it's a theoretical model capable of describing the current state of our sun. That is very important, not only for solar physics, but also because it serves as a sort of benchmark reference for all stellar evolution models. So the standard solar model basically works in this, I create this sort of very simplistic scheme to explain a bit what are the concepts. Works taking some input parameters like the initial mass and the hydrogen, helium, and metal fraction, where for metal, here I intended just all the elements heavier than helium, and including all the physical processes that are needed, like the nuclear cross sections of the reactions that I have shown before, the opacity of the plasma, and so on. It evolves the star for a time equal to the life of our sun, requiring to respect some boundary conditions that are the current observables of the sun, so that the resulting star of this evolution process must match the current radius, mass, luminosity, and surface metal abundances of the sun. The assumptions of this model are so very reasonable. So it assumes that the sun must be in allostatic equilibrium, so that the inward gravitational pressure is compensated by the radiation pressure from the reactions happening in the core, and that the energy is only produced through the very well understood processes of the PP chain and Cno cycle. So offering this complete comprehensive snapshot of the present status of the sun, the standard solar model offers us the possibility to test its prediction basically in two ways. So the first is the helioseismology that refers to the seismic waves propagating inside the sun that can be used to infer the sound speed profile and so the density profile of the star. And the other are the fluxes of solar neutrinos. So given this snapshot, these fluxes of neutrinos can be produced with quite accuracy. But in the recent years, it emerged a sort of problem with the standard solar model, because an improved analysis of composition of the solar surface led to a reduced estimate of the elements of the heavy elements abundance in the sun, which caused a quite significant tension with helioseismological observation. We see here in this figure from the most recent standard solar model released by the Barcelona group that the deviation in the sound speed profile of these new let's call them low metallicity standard solar model is quite significant with respect to the old composition models that we call in this talk high metallicity, here represented with a blue line. The difference in the composition of the sun also led to different predictions of solar neutrino fluxes. We see here in the table the predictions for all the neutrino fluxes in the PP chain and say an overall Cno flux where we combined the neutrinos emitted in the nitrogen 13, oxygen 15, and fluorine 17 beta plus decays. Here in the two columns from the high metallicity and low metallicity solar model, and we see that here we indicate difference, fractional difference, and can reach the level of 20% for boron 8 neutrinos and almost 10% for beryllium 7 neutrinos. So measuring neutrinos, as also will be, this part will be covered in one of the next talks, is a very promising way to try to understand better this apparent discrepancy that is highlighted in helioseismological data. Now, the prediction of the standard solar models then can be used to derive the spectrum of solar neutrinos that is represented here, and it has been at the center of a very long efforts that lasted for more than 50 years by now. So to put the Boraxino accomplishment in a sort of historical context, now I take a moment to highlight what were the major experimental results in the field in the investigation of the solar neutrino spectrum. So the first generation of experiments based on the capture of electron neutrinos onto some target nuclei, so-called radiochemical experiment, were only capable of measuring the integrated spectrum above a certain energy threshold, highlighted here by the endpoint of this bar, which was enough to demonstrate that nuclear reactions were actually taking place in the sun, but not enough to really, and also enough to highlight the fact that the flavor of neutrinos were actually was transitioning during the flight to the Earth, but not enough to investigate with great detail the spectrum. What the Cherenkov experiments were able to measure only the high energy part of the spectrum with an incredible accuracy because of the very large exposure and the very large mass of these experiments. But here there is a lot of space that could be covered by liquid scintillator experiments like Borexino that has a high light yield and therefore a low energy threshold. Here is basically limited by the presence of carbon-14 background that cannot make us go below. But the key point is that with the energy resolution we have, we can separate with a spectral analysis the different component of the neutrino spectrum. So as Alessio already mentioned, the challenge of Borexino is all about radio purity. The detection method is the elastic scattering of neutrinos onto the electron of the liquid scintillator, which makes the experiment sensible mostly to the electron neutrinos because of the charge current possibility of this interaction. And as was already highlighted, the typical interaction rate is of the order of 10 to minus 9 becquerel per kilogram, while the typical activity of water is of the order of 1 becquerel per kilogram. So the key of the Borexino results was the capability of climbing down these 9 orders of magnitude in radio purity through the material screening, purification, and background suppression. So the key point, the first point for this background suppression, of course, was putting the detector on the ground. That is the Laboratorio Nazionale del Gran Sasso, with an overburden of 3,300 meters of water equivalent, which allows for a reduction of the cosmic ray flux of the order of 10 to the, for a factor of 10 to the 6. The energy resolution is at the order of 50 keV at 1 MeV, and the spatial resolution is at 10 centimeters per 1 MeV. You see here a sketch of the detector that was already described in detail by Alessio. We have the detector that is housed inside this water tank that acts like a passive shield for environmental neutrons and gamma rays, and for an active veto, Cherenkov veto for the muons that are still reach the underground laboratory. And here we have that the scintillator is placed in the core, enclosed in a very thin nylon vessel, surrounded by also scintillator that is quenched so that it does not produce light and acts and add a passive shield from the radiation produced by gamma, decays happening in the steel of or in the glass of the PMTs and in the steel of this sphere that supports the 2212 PMTs that read out the light produced by the interaction. Now, a bit of history of Borexino. Borexino, as already said, started data taking in 2007, and for its first phase lasted until almost the end of 2010. Already during the first phase, the phase 1, Borexino was able to deliver some very important results on the PP chain. In particular, the first measurement of beryllium-7 neutrinos after only 47 days of data taking. Also, first evidence of PP neutrinos and the most stringent limit on CNO neutrinos to the moment, and a measurement of boronate neutrinos that, although is as a statistical error larger compared to the ones of large-scale water Cherenkov detectors, had a very low threshold at 3 MeV. So after 2010, there was a purification campaign that further lowered the intrinsic background of the scintillator. And starting 2012, we started our phase 2 that we closed after 2016, and that will constitute the data set that I'm going to present today. Already during the first part of the phase 2 in 2014, Borexino was able to provide the first spectral measurement of PP neutrinos. That is very important because the PP neutrinos highlights the driving mechanism of the PP chain, and so the overall energy production in the sun. And as I said, now after purification with this improved radio purity and a better detector stability, including also the better understanding of our detector response, we're able to provide a simultaneous measurement of all the low energy solar neutrinos and to improve our measurement of the high energy boronate neutrinos. So if we look at Borexino data at the low energy, despite all these efforts to lower the background, we don't see much. Here we see only this, the tail of the decays of carbon-14 that is unavoidable when it comes to liquid scintillator. Then we apply a first cut on the muons to remove short-living cosmogenic isotopes and a fiducial modulo cut so that we select only the innermost part of the detector to remove the influence of external gamma rays and the background coming from the surface of the inner vessel. And here we start seeing things like this peak due to the polonium-210 contaminations, the clear shoulder of the beryllium 7 neutrinos signature, and this bump due to carbon-11. Here in this region, actually, this is quite annoying because in this region there is the endpoint of PP neutrinos and Cno. So we develop a method to remove as possible these events. This is based on the so-called threefold coincidence method, which because carbon-11 is produced typically by spallation of muons that hits carbon-12, producing carbon-11 and at least one neutron. So studying the coincidence in time and space of the passage of a muon track and the capture of the neutron that leaves this characteristic 2 MeV gamma ray, one can evaluate a likelihood for an event to be or not to be C11 based on the recorded muon, the NDX, so for the stopping power of the muon, the multiplicity of neutron captured in the region, the distance from the muon track, the distance from the neutron vertex, and the distance of the neutron vertex onto the muon track. So you see here from this dedicated paper on this method, this likelihood as a function of the visible energy recorded by Borexino. This is exactly the region where carbon-11 is present, and we see that this observable is very efficient in tagging these events. So if we select these events, we see that we suppress quite significantly the bump of carbon-11, but the events that are selected are not completely discarded for the analysis, but are taken in a separate data set. And it is analyzed together with the carbon-11 suppressed one. So now it comes to the measurement of PP chain solar neutrinos. We have two separate analyses for the low energy and high energy boronate neutrinos because of two completely different energy scales and completely different fluxes. So we start here from the low energy one. We analyze the energy range between 190 keV and 2.9 MeV with the goal of measuring PP, PEP, and beryllium 7 neutrinos. We had an exposure of almost 1,300 days and a fiducial volume, once we applied this fiducial volume cut, of 71.3 tons. We use as observable the visible energy, of course, the radial position to be able to constrain the external gamma ray background, and a pulse shape parameter that was already introduced by Alessio for better identifying the positrons from carbon-11 decays. We use also two different response models, the Monte Carlo model and the analytical response model already introduced also by Alessio, to cross-check the results and overall to make the results also more sound. So these are the main backgrounds for the low energy analysis. You see here in red the neutrino components highlighted and dashed lines the main backgrounds. As I told you before, at low energy we are limited by carbon-14. Then we see this peak due to the alpha decay of polonium, to the quenched alpha decay of polonium-210, krypton-85, bismuth, and C11. So bismuth will have a special place in our analysis, especially concerning the Cno. So I will leave maybe the discussion to this background to the next talk. But what we can say is that in our analysis, we studied sensitivity with the help of many simulated experiments. And in particular, we see, I can already say it in advance, that the correlation between the PP, CNO, and bismuth clearly limits the sensitivity of Borexino for the measurement of the PP and CNO. You see here that this correlation is very clear and affects our sensitivity. So for this specific analysis, we decided to constrain the rate of CNO neutrinos to be able to measure better the rate of PP. So we constrained the CNO with the rate expected from the high and low metallicity. So our model, we see here an example of these correlation plots for the CNO expected from the high metallicity. And you see that now the expectation on the PP is much better than in this case. So here are the results of the fit, of the results of the fit on data. Here you see the energy spectrum of the carbon-11 suppressed and carbon-11 pegged data sets that are fitted simultaneously together with the radial spectrum, which distinguish the uniform components with the external gamma ray background that has this very characteristic exponential decay, and the pulse shape. For what comes the...
7 minutes, Daniele.
Thank you. For what comes the boron-8 measurement, the boron-8 flux is much smaller. It's like 3 orders of magnitude smaller than the beryllium-7, and it has a very has a higher energy. So we had to, in this case, to maximize the exposure. So we taking the same data set, data from phase 1 and phase 2. So we start in 2008, 2016, in an energy range between 3 and 16 MeV. The fiducial mass here was basically the entire active volume. So we did not apply any fiducial volume cut, also because the energy range is, the lower threshold of the energy range is so high that most of the radioactive background is already excluded. The data selection here focuses on the suppression of those events that causes a background in this energy range that are mostly cosmogenics. So the data selection was excluding muons and neutron produced by the spallation and the fast cosmogenic isotopes, including the carbon-10. The data set was split in 2 energy regions, H1 and 2, where in the first one, beside boron-8, we also had we expected some background from surface contaminations and neutron captures, while here we only had boron-8 events and neutrons from alpha N reactions. We see here the results of the fit. Here we did not apply a fit on the energy observables, but only on the radial spectrum to extract boron-8 that is expected to be uniform in the detector and background components. You see here, see here in the high energy one, the boron-8 signal and the background from surface contaminations, while here in the high energy region, we only have the boron-8 and this background coming from neutrons produced in alpha N reactions in the PMTs or in the steel of the sphere. So all things considered, our results on the PP chain investigation are summarized in this table, where beside the predictions of the standard solar models, I put our findings. We were able to measure the PP neutrinos individually with an accuracy of around 11.6%. That is the best measurement by now. We also were able to measure PP neutrinos. Here we report 2 results because this depends quite strongly on the assumptions of the CNO flux we used to determine it. But both of these results showed that the absence of PP neutrinos is actually excluded with a significance higher than 5 sigma. We have then our measurement of beryllium-7 with an accuracy below of 3%. sorry, at the order of 3%, and our measurement of boron-8 with an accuracy of 8%. So these are both better than the accuracy in the prediction of the standard solar model that makes these results very interesting. So coming now to the short preview of the astrophysical implications of Borexino results, that also will be a topic of one of the next talks. So maybe just I will go quite fast, so just to give you a preview. So the first point is the test of solar luminosity, because once we measure all the neutrinos, we are also able to infer what is the rate of nuclear reactions happening in the sun. And since we know quite precisely what is the energy released in each one of these reactions, we can then infer the power of the sun from the neutrinos to be compared with the luminosity of the sun measured with traditional photon output. And we see that these two measurements actually agree quite well. So and this proves that basically the nuclear origin of the solar power, and that the sun has been in thermodynamic equilibrium over the last 10 to the 4, 10 to the 5 years, since the photon output that we see now on the surface is the result actually of reactions that were happening 10 to the 5 years ago, because this is the time it takes to the radiation to reach the sun's surface with once one takes into account the opacity of the sun. Another point is the relative intensity of the two main terminations of the PP chain. So we said before that the main termination of the PP chain actually did not produce neutrinos, but others do. So here I just present a reduced scheme of the PP chain, where we neglected the PP and boron-8 reactions because they contribute overall not so much to the dynamic of the chain. And with this scheme in mind, one can, and also assuming the local equilibrium between the deuterium and helium-3, sorry, of deuterium and helium-3, one can derive the relative intensity of the PP1 and PP2 branch as this ratio. And we see that the result of Boraxino, 0.178, this error, is compatible with the prediction both from the high and low metallicity solar model. Also, Boraxino can test the high and low metallicity with the PP chain results in another way, because of the different core temperature predicted by the high and low metallicity standard solar model. The fluxes of beryllium-7 and boron-8 are significantly affected because of the peculiarity of these two reactions that are quite strongly dependent on the temperature. So you see here these two ellipses showing in blue and red the predictions of the high and low metallicity. Here you see Borexino results, and we computed a p-value for both the high and low metallicity, which is, I mean, we show a good level of compatibility actually with both models. But also we performed a global analysis, including all solar neutrino data, which moves, which reduces a bit the significance of our very mild preference for the standard solar model, with high metallicity. So we performed this also this hypothesis test that we can quantify our preference using the PP chain data to the standard solar model with high metallicity to have a significance that is below 2 sigma, so not very high. But what is, I think, is interesting to highlight is that we are now basically dominated by the uncertainties in the prediction of the standard solar model. But I suggest to stay connected for Aldo Savinelli's talk to hear more about this. Another thing.
We only have 1 minute.
Okay, I'm just closing. So another interesting topic here is that we can also test also the MSW large mixing angle oscillation scenario, so that with the implications in neutrino physics, because this is the first time that with just one experiment, we have been able to investigate the survival probability of electron neutrino, both in the vacuum oscillation regime that is the one of low energy neutrinos, and in the region where Msw Effect plays a very important role, and so so enhancing the oscillation of boron 8 neutrinos. But to hear more about this connection with the oscillation physics, also there is a next talk by Marco Pallavicini, so I won't say much more. So in conclusion, the solar neutrinos are still an essential tool to study the behavior of the sun and all of our stars by extension, as well as oscillation physics. So Boraxino in this field has been the key player for the past 15 years, and the comprehensive measurement of the entire PP chain that I've just presented, I think, is one of the greatest scientific accomplishment of the field in the past years. So here I think that I stop, and I thank you for your attention.
Thanks a lot, Daniele. We just finished in time. Unless there are urgent questions that I do not see, it's time to move to the next talk by Marco Pallavicini about the electron-neutrino survival probability in the low energy range, the one accessible by Borexino, 5 keV up to 15 MeV.
Thank you, Gemma. I start the sharing. Can you see it?
Yes, we see it.
Okay, so I switch to full screen. So thanks to all. I will, of course, partially repeat what was said, but I will go quick on some of the parts, and I will focus on the impact on the low energy measurement of solar neutrinos with the electron survival probability, which is the Msw oscillation effect that I will explain. So this is a very quick summary. Of course, I will summarize a little bit the science, few words on the technology, because the key element of the quality of the measurement we obtained is based on the purity. And then, of course, I will focus again on PP chain neutrinos and the Msw mechanism and how we extract the survival probability. So the key element is the picture on the left. I will not speak about the Cno cycle because it will be covered by others and it's not relevant for electron survival probability measurement. What is relevant is the fact that the PP chain has several neutrino components, and these neutrino components have very different energies. The main flux is from the PP, which is very low energy, essentially below 400 keV approximately. And then there is the PEP neutrinos that is small, but it's relatively high energy, about 1 MeV, as we will see. And then there are two lines, one coming from the electron capture of beryllium-7, which yields a nice monochromatic line at about 800 keV, and the boron-8 neutrinos, which are a minority in number, but are the easiest to measure, especially with the non-scintillator detector, because they are high energy and they were very precisely measured by Cherenkov detector. And of course, the boron-8 is good because it gives you a high energy neutrino that you can measure. There is actually an even higher energy neutrino, which is called the HEP neutrinos, but that flux is way too low for existing technologies, was not measured by anyone, and I will not speak about it. Of course, on general grounds, there is an abundant flux of neutrinos from the sun that brings out about 2% of the total energy. A key element of the extraction of the electron survival probability is the theory. I will not cover it in detail, but of course, as I will say at the end, you cannot with Boraxino extract the electron survival probability without precise knowledge of the expected electron neutrino flux. I should mention that, of course, from the picture above, electron neutrinos only are emitted by a sun. So the sun is a totally pure electron neutrino flux at the origin. And of course, the purpose of the theory of the model is to provide a precise prediction of these fluxes. This is not an easy business. Of course, the theory was developed by the impulse of John Bacall, who led a very important and long-standing effort. And now the group of people that he initiated and formed, and others, of course, there are many now important theorists who are contributing to the refinement of this model. You see in the plots below an example, just for the illustrative purpose, of the improvement of a prediction over time of several solar standard model fluxes. And this improvement is the result of a lot of work in many directions, improvement in the knowledge of the cross-section because, for example, of measurements done in underground labs and in accelerators, improvement in the quality of the numerical simulation of the mechanism, better understanding of the thermal equilibrium of the sun, which is mostly due to the opacity, to the capacity of the sun to release the power through radiation of photons in the solar core. So the model by itself is an evolutionary one in which you assume some initial condition, you put into the equations all the physics you know with the uncertainties of the parameters you don't know, and you compare with the sun you observe today. So it's a complex calculation that now has reached a high level of precision, and this is a key element for the extraction of the survival probability. The flux that you expect at the sun is this one, is different energy components. This is a plot in the terms of neutrino energy. Of course, you never measure neutrino energy with any detector. You measure the energy deposit. So as we will see, this plot is deformed significantly when you translate it to detector response. But as far as the theory is concerned, this is the flux. You have pp neutrinos, more abundant than any other, but lower in energy. You have 3 monochromatic lines coming from beryllium-7, which has 2 lines, and the PEP, which is a final state 2 body. So the neutrino is monoenergetic. And then you have the boromate neutrinos, which has much lower in number, but much higher in energy. And both because there is less background in the boromate region and because the cross-section is higher, actually measuring boromate neutrinos is slightly more difficult than the others, but not much. So the difficulty, as we will see, is similar. One point about which oscillation we are talking about. The sun is big and hot, which means that coherence is completely lost. You do not measure vacuum oscillations, because if you took into account vacuum oscillations only, essentially you would expect the survival probability to be a constant, depending only on the mixing angle and not on the masses. The reason is that because the size of the sun core is much bigger than the oscillation length with any reasonable parameter set. And the same second reason, but they are both equivalently important in destroying any coherence. The sun is very hot, and the typical thermal energy is much more than the masses and the mass gaps. So vacuum oscillation are completely lost, and what remains would be a constant. But that is not the case, because as was discovered by Wolfenstein and developed by Mikheyev and Smirnov and later others, but we now call it the Msw effect, electron neutrinos, which are their whole flux at the beginning, propagate through matter. They encounter electrons. The propagation amplitude is not the same for electron neutrinos and mu1 and tau neutrinos. This generates a phase shift, which generates an energy-dependent survival probability. There is no easy analytical formula for that, so I'm not elaborating on the theory. I will just show the plot of the curve, but the energy dependence of the oscillation come from this very important effect. The effect in principle could be present also in the propagation within the Earth. This is not the case for low energy neutrinos, and Boraxino proved that there is no matter effect in the beryllium-7 line, which is consistent with what you expect with the theory, because as we will see, the theory predicts a large Msw effect on boromate neutrinos, a small amount of effect in PEP and beryllium-7, very small, and essentially no effect on PP neutrinos. And the Boraxino data confirm this prediction. Boraxino is at Gran Sasso. I will go very quickly on this one. I just show the nice coat we added to the tank a few years ago, which proved to be a key element for the Cno measurement that others will cover. Detectors, I assume it's already well described, so I go quick, but the key point is that through the concept of graded shielding, we have the lowest radioactivity piece of matter ever built, which is the Boraxino fiducial volume. The liquid within the inner vessel is by far the less radioactive bulk matter element ever built on Earth. This is the picture of this bulk seen from cameras that look inside. This picture was taken in 2009 during a calibration campaign, which was extremely important for what I am saying, because the high precision measurement of all neutrino components come from a deep and, let's say, complete understanding of the detector response in energy, position, and general behavior. And this was obtained through a very intensive calibration campaign on one side and a big effort in Monte Carlo simulation to be sure that the Monte Carlo reproduce very well the detector response. So another key point of the PEE measurement is, of course, understanding that there is no capability for Boraxino to distinguish event by event the neutrino type. The three neutrino types scatter on electrons. Kinematically, the events are essentially identical. The angular distribution is not exactly the same, but it's a very minor effect. What differs is the total cross-section, which is about a factor 5 higher for electron neutrino with respect to mu and tau neutrinos. But you cannot tell which is which on event-by-event basis. So what you measure is a rate. And I will show in the end that, fine, you can still get some information about the number of electron neutrinos and the number of mu neutrinos, but you need the initial flux as an input, so you need the theory. You cannot do it experimentally by itself. The second important element for PEE measurement is that this technology, the liquid scintillator technologies, while creating a lot of difficulties because you need the very low background, but you have sensitivity to all neutrino components because the energy threshold is in principle very low. The hardware threshold could be as low as a few tenths of keV. We normally run with the triggering threshold of about 40, then we made it a little higher during the lifetime of the experiment because of PMT loss, but the trigger threshold was about, let's say, 50 keV, while the analysis thresholds, as we will say, is higher, but not because of limiting the capability of the detector, but because of the carbon-14 background, which hides completely neutrino signal below 200 keV. Gemma, you complain if I'm going slow. Probably I am, so I go quickly. The comment about the spectrum, you go from the left to the right by switching between neutrino energy, which is an unknown quantity, to the energy deposit of the electron scattering into the scintillator, which is what you measure, and you see what you would expect expect ideally from all solar neutrinos that spectrum, including PP, beryllium-7, PEP neutrinos. Boromate is not shown in this plot, but it's higher in energy. What we measure was already said. I go quickly. We measure energy through the total amount of light. We measure position by time of flight. And we can distinguish alpha and beta particles, or possibly in some cases, beta and beta plus plus particles by pulse shape discrimination. Again, quickly on the backgrounds, we made a huge amount of work over 20 years to fight the external background, which means a neutron and gammas penetrating into the detector or originating from the materials. Internal backgrounds, which means radioactive contaminants dissolved into the scintillator. We made a very good job on many of them, most of them. Essentially, the background are due to uranium, thorium, potassium, argon-39, and also beryllium-7 is 0. We have no evidence in the data. We have a residual small amount of krypton and lead, polonium, bismuth chain. I will not comment too much on that, but because those components are very important for CNO measurement. The krypton is important also for the PP and beryllium-7, but essentially these backgrounds have been kept low enough to make the measurement solid and high precision. Cosmogenic, I will cover very quickly because it's relevant for PEP neutrinos, but you have radioactive elements produced by muons crossing the detector. One nice trick we invented is the so-called threefold coincidence, in which neutron, muon, and carbon-11 are all correlated in space and time to identify the carbon-11. This is an example. For other cosmogenic, which are important for boromate neutrinos, we use cuts on essentially killing the detector around the muon in time and space to remove these cosmogenics. Again, specific analysis that can be found on boromate papers. And then I will go quickly on this because it's not relevant for PEP neutrinos, but it's super important for CNO neutrinos, which is the migrating background. So the background originating from the vessel and moving toward the inner vessel. It's a super important topic, but I'm sure it will be covered in detail by CNO speakers. So I just mentioned, but skip it. So the numbers, why we could measure PEE survival probability through neutrino components measured one by Boraxino for the first time, except boromate, is the background. You see from the numbers that we already got much better than design goals, because the design goal of Boraxino was 10 to the minus 16 gram over gram in uranium and thorium. And we actually did better even at the beginning, but then we improved by another almost 2 orders of magnitude through purification in loop mode, using water extraction to remove metals and using nitrogen sparging to remove krypton and argon. This is the plot of the data and the cut, which is better understood here. The black, of course, is the raw data. You remove muons and cosmogenic and you go to the blue. And then you cut the fiducial volume. So you select event only in the central part and you go to the red curve. And the red curve is very close to the ideal one, except the peak of polonium-210, which is not very problematic for PP chain measurements. And it went away through essentially decay. The analysis of the polonium peak is again a key element of CNO analysis and will be covered by others. The carbon-14 is indeed very important for the PP measurement. Again, there is absolutely no time to go into the details, but the PP measurement is based on the very careful understanding of the spectrum in the so-called valley, which is the region that we call between the polonium peak and the carbon-14 tail. Pile-up of carbon-14 was a key issue to be understood very carefully and to be very carefully simulated and modeled. And finally, we could extract the PP counts from them. Beryllium-7 is easy. It can be seen by eye. That is the beryllium-7 shoulder, very neat. PEP neutrinos and boromate neutrinos are not visible easily in the spectrum. There are a component of the high energy part above essentially 1,000 photoelectrons, which is close to more than 2 MeV. We measured boromate neutrinos above 2.8 MeV in the final paper. And PEP neutrinos are extracted through the TFC removal by the spectrum, but again, cannot be seen by eye, so you need the spectral filter to do it. I go quickly on some of the results.
5 minutes.
Yes, yes, so it's okay. The beryllium-7 we measured several times. This is the 2011, what we called the final measurement, although in 2018 we made a refined, again, analysis with a comprehensive paper, but this was the first high precision measurement that we published in 2011 by essentially fitting the spectrum in that region with and without the alpha beta removal of the polonium peak. You see these two plots are the same plot. In the left part, the polonium peak is left visible and fitted. In the right part, it is subtracted using alpha beta discrimination and giving consistent results. This is what we did in 2011, giving the first high precision measurement of beryllium-7. The PEP measurement came in 2012, 2013, and the key element was the threefold coincidence I already mentioned. That is important to identify carbon-11. Then you can decide, and we did both in several instances of the analysis, either you can cut, so you can remove the carbon-11, or you can use this information as part of a multivariate fit in which you use the capability to disentangle carbon-11 through this pulse shape. You see here that because of the fact that the positronium needs some time to be captured and then generate a scintillation light, there is a slight time difference profile between the beta and the beta plus, which say electron and positron, and this can be used to add some additional information that is beneficial to subtract or to take into account in a multivariate fit of the carbon-11 component, which finally gave the 2012 result on PEP neutrinos, which again was refined in 2018 in the comprehensive paper, but the first precision measurement of PEP came in 2012. And this is what we did in the comprehensive and also Cno Nature papers, in which we finally achieved the capability to make a complete fit. The previous analysis I mentioned were made one by one by looking at specific cuts, specific analysis, specific fits of each individual component. Then we reached, and this was very important, sufficient understanding of the detector of the data of the spectra to make a global fit, which we did in 2018. And the important message of this plot, which is complex and would require a lot of time to be completely explained, is the fact that we fit the data without unknown components. It's normal practice in many experiments to add, let's say, polynomial or exponential of any kind of unknown background to take into account not understood components. We don't need it. This fit is completely done with the known, understood, and directly measured, or at least components that can be extracted from the data. And so this is the key conclusion on which we can spend some time. The 4 beryllium PP chain lines, which are the PP, the beryllium-7, and the PEP and the boromate, are shown there. Of course, I could not go into the detail of each measurement because way impossible in 20 minutes, but I prefer to focus on this plot and give the main message. Of course, you see the numbers of the rates quoted into the plot. And you can see very quickly by eye that in most of the cases, the precision of these numbers is much higher than the error bars. The reason is the one I highlighted at the beginning, that we measure count rate and not flux. So to get to the PEE, you need the flux. You can do it by the formula that is shown below, because you know the cross-section. Sigma E and sigma mu tau are very well-known standard model cross-sections with very small errors. The PEE is what you want to extract, but to extract PEE from the rate, it's a simple algebra, but you need to know the flux at the sun. So you need the original electron flux for each energy component. So you need the theory. That's why the error bars are larger, because in order to extract the information, you need to know what is the flux with its own uncertainty. So the quality of the work we could do so far is this one. There is room for improvement, because clearly, as I will show in next plot, theory still allows for deviation of the PEE. Of course, the pink curve is what you expect from the solar standard model, including the uncertainty on the oscillation parameters, as we know today. From this plot, you also extract a hint of the metallicity, because each PP, beryllium-7, PEP, and boron-8 flux depends indirectly on the metallicity, because if you change the metallicity, you change the theory, you change the temperature, you change many elements of the sun, and fluxes are affected by that. But our data is still not conclusive. There is a preference for high Z, because it's clearly by eye that the high Z is preferred, but the precision is not sufficient to draw any firm conclusion. It's a matter of taste to decide if you want to call it a hint or a preference or whatever, but definitely Boraxino data cannot exclude yet the low zeta value of the metallicity. So I go to the conclusion that I leave you for your reading. Interesting is an example of theoretical work that is still in progress. This is a plot of Maltoni and Smirnov. It does not include the super recent Boraxino measurements, but they are not very different from the one shown here. So it is clear that beyond the, let's call it the standard model, there are many theoretical models, including non-standard interaction or including sterile neutrinos or both, which could affect the PEE and be compatible with Boraxino data, which is a good message for the future. We made a fantastic journey, but as it's well known, our journey is over. Other experiments will have to do better, and I hope this will happen. Thank you.
Thank you, Marco, for this very comprehensive talk. It's time to move to the next presentation by Barbara Caccianiga. She will talk about the most recent measurement of Boraxino, which is the detection, the first detection of neutrinos from the Cno cycle.
Marco, can you stop sharing the screen?
Absolutely. Yes. Thank you.
Can you see my screen?
Yes, now we see it.
Okay, so I can start. Good morning to everybody. I will focus my presentation on the last result of Boraxino. I would say last but not least, in the sense that it concerns the direct experimental detection of the Cno cycle. You have heard from the previous presentation about our work on the proton-proton chain neutrinos, but here I will focus only on the Cno cycle. And as you can see from this plot, the relative importance of a Cno cycle in the PP chain depends on the temperature of the core of the star. And for the sun, as we have heard before, the Cno cycle is dominant, and but it's dominant in non-massive stars. So the Cno cycle, although it's not important in the sun, is crucial for the energy production in the stars and in the universe. Therefore, it's important to have an experimental proof of its existence. This is what Boraxino has done. Besides that, the importance of the Cno cycle is also related to solar physics, in the sense that the Cno cycle can help disentangling the so-called solar metallicity puzzle we have heard about before. Just summarizing briefly, as you know, the metallicity of the sun is the content of elements with Z greater than 2, and it's a crucial input parameter of the standard solar model. It is obtained from spectroscopic measurement of the photosphere. And as you know, the most recent reevaluation and most trustable reevaluation of metallicity led to a value which is lower than the previously obtained one. And if you use this newest value as input in the standard model, then the standard model gives in output which are at odds with the new measurement from Seismology. On the contrary, if you use the old high metallicity as input, you would find results which are perfectly goes under the name of solar metallicity puzzle. And what can solar neutrinos from the Cno cycle tell us about this? Well, the predictions for Cno neutrinos depends on the input metallicity. In two ways: directly, because the Cno reactions depends directly on the content of carbon and nitrogen in the core of the sun, and also indirectly, because the Cno reaction depends on temperature of the core, which in turn depends on opacity, which in turn depends on metallicity. So if you take the prediction from high metallicity model, standard model, and low metallicity for all the type of neutrinos from different reactions, you can see that the last three lines are the Cno neutrinos, and that may have differences as large as 38%. So you can see that measuring the flux of Cno neutrinos could provide a crucial input to the solve this puzzle. About Borexino, of course, you have heard about Borexino many times today, so I won't go into the detail except of saying, of course, its core is made of 300 tons of liquid scintillator, which is the active medium. The light is observed by 2,200 photomultiplier tubes. And then I would like to highlight another small piece of hardware, which is actually very important for what I'm going to say next. That is the nylon vessel, which is the container of the scintillator. It's a very thin nylon, which is 4.25 meter radius. And I'm highlighting this especially because the radioactivity, which is very small, but still higher than what we would like, is actually something that we had to deal with carefully in order to make the Cno neutrino measurement, and this I will discuss later on. You have heard about the story of Boraxino. I will focus only on what we call phase 3, which is from 2016 until 2020. Basically, we are still taking data now, but the results I'm talking about are stopped at 2020. So, by the way, we have another year of data still to analyze. But what I would like to say is that the reason for which we only use the phase 3 data for the Cno analysis will be clear later on after I discuss some of the details of the analysis. Unfortunately, as mentioned just now, this long story is going to end soon because in September we will stop. So you have heard from Alessio and the other how good is the radioactivity for Borexino. But even in these high radio purity conditions, we still have the ground events contaminating our solar neutrino signal. So we need to perform to apply software cuts to data in order to remove as much background as possible. And the cuts are the same for the CNO analysis with respect to the one used for the other analysis described by Daniele and Marco. So I won't go into the detail, just highlight the points which are foremost of interest for the CNO analysis. Here is how the energy spectrum looks like if you were not to apply selection cuts. Just for reference, 1 MeV is approximately at this point. This is in our variable, which is number of hit PMCs. But you need to apply cuts. And the one I want to focus on is the fiducial volume cut. What is it? Simply, we, by software cut, we select only the innermost part of the detector. Here I'm describing it as if we selected a spherical innermost volume. Actually, it's more complicated than this, but just to tell you the principle. So the idea is that we want to stay away from external background as much as possible, especially background from the photomultiplier tube, but also, again, I want to mention the background from the vessel. What I want to anticipate here is that the radioactivity which is on the vessel would be dangerous for our analysis. And this is also one of the reasons for which we apply the fiducial volume cut. Unfortunately, we realized that changes in temperature of the detector causes convective motion of the fluids. And this convective motion are strong enough to detach some of the radioactivity which is on the vessel and bring it inside the fiducial volume. So I just anticipate here one of the problems that we have to face and why we had to thermally insulate the detector. But now, as mentioned before, the fiducial volume cut is able of showing immediately in our data by eye the beryllium-7 neutrino shoulder, as you can see here. But unfortunately for Cno neutrinos, it's another story, because here are the data for the data set that we are using. So phase 3 from July 2016 and February 2020 after selection cut. And while you can still see the beryllium-7 shoulder, you can ask yourself, where are Cno neutrinos? And this is what is predicted by the simulation. Cno neutrinos should look like, and it's really, they are submerged by residual backgrounds, like looking for a needle in a haystack. And how we do that? Well, part of the analysis is exactly this, most of the analysis is exactly the same as the one described by Daniele for the proton-proton chain neutrinos. We exploit the difference in the energy and radial distribution of signal and background to separate them. And how do we know the spectral shapes, the radial shape for each component? By Monte Carlo simulation, which were detailedly explained by Alessio, so I won't go into the detail. This Monte Carlo has been tuned on calibrations, as mentioned also by Alessio Marco. So we have a very solid understanding of the response of the detector. And here is an example of the simulation for signal and background that come for the distribution in energy that we use for the fit. So a fit is performed to the energy distribution of events assumed to be the sum of signal and backgrounds. As I said, the shapes are those determined with Monte Carlo simulation, and we include in the fit also the radial distribution of events. And the rates of each species, almost all the species, as will be clarified later on, are the free parameters. So there is an extra problem for what concerns Cno neutrinos with respect to the other analysis discussed before, which is the bismuth-210 problem, let's say. So what is bismuth-210 is a radioactive isotope which decays beta with the spectrum, energy spectrum, which is the blue curve you can see here, which is very similar in shape for what concerns the shape to the Cno neutrino. So the spectral shape is so similar that the fit can hardly distinguish between the two contributions. Also, the rate of Cno signal and bismuth is similar to some extent. So it's very difficult to disentangle the contribution if you want to really take out the rate of, I mean, you want to be sure you are seeing Cno neutrinos. So our strategy was to try to determine the rate of bismuth independently from the and constrain it in the fit to see whether there is room for Cno neutrinos left. How can we do that? So bismuth is not by itself. If it was by itself, it would be the case in 7 days and it would be no problem. Unfortunately, it's continuously refurbished by lead-210, which unfortunately has a long lifetime, instead 33 years. And so there is this small chain, which is lead, which goes into bismuth, bismuth, which goes into polonium, polonium, which goes into lead-206. At secular equilibrium, the rate of polonium and bismuth should be the same. So if we measure polonium-210 rate, then we can, in independent way from the fit, we can then have a handle on bismuth. Why measuring polonium-210 is easy? Because polonium-210 decays alpha, and it's a peak. You can see it by eye, it's easily recognizable. And also, as you heard before, we have capability to distinguish the alpha and beta signal, and polonium-210 is decays alpha. So these things seems easy to do then, but if you look at the count of the polonium rate as a function of time since 2012, you can see something strange in principle. You would expect a flat rate if everything was in secular equilibrium. If lead-210 and its daughters were in secular equilibrium, you would find you would expect a flat rate. You are not seeing this. You are seeing a very steep descent compatible with the lifetime of polonium-210. This is because we have introduced polonium-210 out of equilibrium, which fortunately decays with the lifetime of polonium of 200 days. So in principle, you can wait a couple of years for the polonium out of equilibrium to decay, and then you expect to have a flat line, which corresponds to the equilibrium value. But you can see easily that this is not the case. You can see these wiggles here, this large fluctuation of the polonium values, which are puzzling. What is causing these large instabilities of the polonium rate? We realized, as I was mentioning before, that they are strongly correlated to temperature variations.
Barbara, you only have 7 minutes.
Okay. This is interpreted as the vessel is contaminated with lead, and so all this is daughters, and temperature variation are causing convective motion, which bring polonium-210 inside the fiducial volume. Fortunately, there is no evidence that these convective currents also bring lead-210, fortunately. But unfortunately, they bring polonium-210, which means that the condition of secular equilibrium is broken, and the polonium that we see inside the fiducial volume is the sum of two contributions. One is the one that we want, which is related to bismuth-10. The other instead is polonium out of equilibrium coming from the vessel. So this is what the idea came in 2015 when we realized that we need to thermally stabilize the detector with this nice cover that you can see here in this picture with 20 centimeter thick layer of rock wool. The work was completed in December 2015, and actually it was successful because you can see from the plot here from when the installation was completed in 2016 that we have a much more stable behavior of polonium-210. However, the situation is still not completely stable. I mean, there is still some residual convective currents. But we were able, you can analyze this plot, which is a bit complicated. I can try to explain it. On the x-axis, you can see the time. On the y-axis is the vertical direction. So on the top, the detector top, and on the bottom, the detector bottom. And the color code is the amount of polonium. Red means a lot of polonium, blue means little polonium. So you can see that before insolation, there was big injections of polonium, which had a really seasonal dependence. After insolation, this has reduced a lot, even though there is still some injection, as you can see from the yellow part here. If you analyze carefully the geometry of this, the distribution of polonium, you can see that there is an innermost region almost free of convective current that we call low polonium field. And of course, we cannot be sure that there are no more convective current, no more polonium coming from the vessel. So we basically, by looking at the minimum polonium rate in this region, we can have an upper limit on the bismuth rate. And this is the result we get, 11.5 plus or minus 1.3 counts per day in 100 ton. And this is what we use to constrain in the fit. So we apply all the selection cut, the same that were used for the PP analysis, but on this period of data, of phase 3. And then we apply the multivariate fit, but constraining the bismuth rate to the value that we just found. This is the result of the fit. The dots are the data, and the pink line is the result of the fit with the result on CNO in red. And this is the rate we measure, 7.2 plus 2.9 minus 1.7 counts per day in 100 ton. Of course, we studied carefully all the systematic errors related to this measurement, which is very complicated. 4 systematic measurement, a systematic error associated to destruction of the bismuth upper limit, which are included in the error we put on the constraint, on the fit condition. The most annoying systematic is the one associated to the non-perfect knowledge of the energy distributions. So we produced the toy Monte Carlo in which we injected deformation in the energy distribution compatible with the result of the calibration data, but just to see the effect they had on our fit, and we quote the result in the systematic error. So looking at the log life Q profile for CNO, the dotted line is the one without the systematic error, and the solid one is the one you should consider, which includes also the systematic error. You can see this is the result with the best fit we get, and you can already see that we disfavor the hypothesis of CNO equal to 0 with 5 sigma significance at 99% confidence level. And you can see, however, that the result, which is the error on this result, which is the gray band here, is large still, and so we cannot discriminate between high and low metallicity. Low metallicity is the one with the error band, and this is the high metallicity one. So in conclusion, after many years of hard work, Borexino has actually been able of detecting neutrinos from the Cno cycle in the sun with a significance of 5 sigma. And this gained us also the cover of Nature, and we published this result on Nature in November. With this result, Borexino has completed the real-time picture of the sun, measuring both the processes that sustain it, the PP chain and the Cno cycle. And I also would like to remind what I said at the beginning, that not only this is important for the solar physics, but we have proved for the first time experimentally the existence of the Cno reactions, but never proved it experimentally in the. And I'm finished. Thanks to everybody.
Thanks a lot, Barbara. As we have no question, we move to the next talk by Aldo Serenelli, and we are moving from the results to their implication on the physics of the sun.
Hi, let me share the screen. Okay. Can you see my screen?
Yes.
Okay, thank you. Okay, so thanks very much. I will talk about the implications of the PP chain and Cno cycle measurements for solar physics. And yesterday, Francesco Villante gave this presentation. Today it's my turn. But I would say most of the hard work in preparing the talk has been done by Francesco. Okay, so let me go to the first image. Okay, so the sun has, we can observe the sun in very different ways. We have the fortunate situation only for the sun that we can actually observe it, of course, with photons, also with helioseismology, which gives us a very nice picture of the solar interior, but also with neutrinos. And as such, there's a very important benchmark for not just for solar physics in general, but for all stars in general in the case of the sun. And therefore, its importance is fundamental in a very broad range of astrophysics, also particle physics, but yeah, so it's a very important object to study in lots of detail. The talk is mostly related to standard solar models, though most the qualitative results apply also to non-standard solar models where other stellar physics is included there. Okay, so we can comment on this if you want at the end. But here, as I said, we refer to the standard solar model, which as such is a very well-defined framework where we solve the stellar structure equations with only 3 free parameters, which are related to parametrization of convection and the initial composition of the sun. And these 3 free parameters are fixed by 3 constraints, which are usually the solar radius, the solar luminosity, and the metal to hydrogen abundance in the photosphere at the present age of the sun, which is well determined from radioactive measurements in meteorites. And as such, the model has a lot of predictive power and can be falsified by different types of observations, including solar neutrinos and seismology. Okay. Of course, building a model requires a lot of input physics. As you are well aware, among these, nuclear cross-sections are crucial for predictions of solar neutrinos in particular.
Excuse me if I interrupt you, but I don't see light changing. I don't know the other.
Oh, okay.
I don't know. Is it only me? When
okay.
No,
I have
it's
some
not
stop.
on you.
Okay. So, okay, let me stop sharing and reshare again, okay?
Yeah, try again.
Strange. Now?
Well, try to change. I mean, now I see another slide, but try to change.
Go?
Yes.
Okay, perfect. Sorry about that. It was changing for me, so. Okay, so, okay, so let me finish here. So, yeah, so we need a lot of input physics there. In particular, nuclear cross-sections are very important, and the most uncertain one for solar physics, but stellar physics in general at the moment is the radiative opacities, to which we will devote a few slides in this talk. As you are very well aware of and was already mentioned in previous talks, we have the solar abundance problem, where development in spectroscopic techniques taking place mostly during this century, including 3D model atmospheres, non-LT treatment of line formation, improved atomic data, has led to a reduction in the abundance of several important elements when determined from the solar spectrum. And in particular, the Cno elements are the most affected, and they are the most abundant, or among the most abundant. So that has created a bit of a conflict in terms of what the actual metallicity of the sun is, because the reduction in the solar metallicity carried out by these spectroscopic measurements create a lot of problems in the solar interiors, as you have already seen, and I will mention briefly. Now, the impact of the abundances in the metallicity in the sun is basically through the radiative opacity in the solar interior, so below the convective envelope. Right? Metals do not really matter for the equation of state in terms of the small details, maybe, but it's not something relevant for this presentation, at least. They regulate the opacity, as I mentioned, about 30% of the opacity, or half of the opacity. Half of the total opacity in the solar core comes from metals, and this fraction increases as we move towards the outer regions, and below the convective envelope is about 80% coming from metals. Also, as you well know, the Cno elements in particular control the efficiency of the Cno cycle. In particular, in the case of the sun, carbon and nitrogen are the most important in this case. But the focus is here on the opacities mostly, and because changing the opacity by changing metallicity affects the temperature structure in the solar interior, and this can be measured exactly by helioseismology, and is reflected in the sound speed discrepancy that we see when we use the low metallicities, here shown as red. It was already shown before as well. So with the result that we have this conflict, right, between the low metals observed by spectroscopy and the results from helioseismic diagnostics that we are very well aware of. But the thing to keep in mind always is that the impact of metals is through the opacities. Okay, so there is this degeneracy between those two quantities, which is very difficult to break. Now, of course, the solar abundance problem, one can think of a crisis, and as some people say, every crisis is an opportunity. I'm personally not so sure about that in a general context, but it might well be the case here. Of course, one might wonder that the new abundances may not be correct. Certainly, the spectroscopic analysis has a lot of steps in going from an observed spectrum to an abundance determination. This is very strongly model dependent as well. It depends also on the quality of the atomic data you have, and the model atmosphere you use, and the synthetic models for formation of the spectral lines one uses. So there's a lot of things to be said about that. But the consensus is that even if the spectroscopic analyses are not perfect, it will be very, very unlikely that the previous results, the high metallicity values, would be restored by some further development. Okay. It might also be that the properties of the solar matter are not correct in our current understanding, in particular opacity. Okay. So there has been very nice activity on this field, which is a very difficult one, because you either rely on very complex theoretical calculations on very difficult experimental setups, for which there are just a few that have been carried out so far. Okay. But this is currently, I would say, the Achilles heel of the whole standard solar model, or even non-standard stellar models in general. Yeah. There are, of course, then more non-standard effects that could be some additional mechanism transporting energy in the sun other than radiation and convection, for example, related to dark matter in the solar interior. And one might also wonder if the idea that the sun went initially through a fully convective phase that completely homogenized its composition might not be correct as well. And so there is something to be learned about the very early evolutionary stages, in such a way that the interior and the envelope did not have the same metallicity, or the same composition in general in the very early stage. But this is still something speculative. Okay. But eventually one can use the solar results, neutrino results in particular, to try to learn a bit about these possibilities. Okay. Now, related to the solar abundances, as I said, the 3D models and so on and so forth, they continue to be revised, improved, but results are not really changing that much. There has been a recent complete revision of the solar composition by Aston. Again, results have not really changed. Okay. There is a very extensive work which will be public very soon in Bergman 2021, revising oxygen, just oxygen, which is the key element in the end, but trying to do a very systematic analysis of all possible uncertainties and so on, this leads to a somewhat larger value of oxygen, as you can see here, 875 compared to 869. Okay. Still not enough to solve the solar abundance problem, okay? But at least it shows that also in that field, things are not so fixed, and that further work is interesting, okay? Now, as I said, there is this degeneracy with opacity. So in terms of opacity, the problem is that we rely on theoretical calculations. Experimentally, the only result that applies directly or almost directly to conditions in the stellar interior are those published by Weil in 2015, taken at the Sandia lab. And here you can see in black the opacity, the monochromatic opacity for iron, taking at conditions very similar to those at the bottom of the convective envelope. And you can see in the different colors the comparison between models and the experiment. And you can see a very strong disagreement. You can see that here the quasi-continuum is very badly reproduced by models. These opacity windows, for example, here at 12 angstrom, are also very badly reproduced by models. And the lines are also wrong in the sense that they are too narrow compared to data. Right? Of course, here one worries about the locations where the opacity is low, because that's where photos go through, right? So this quasi-continuum discrepancy and these windows here, they are really a problem. And all the models fail. Now the question is whether there was some systematic uncertainty in the measurement, some systematic problem. And so the same group tried to look at this by performing additional experiments in chromium and nickel. Chromium, because it has an analogous configuration to iron under these conditions, which is an open L-shell structure. Okay, and nickel just to look at a different configuration, because nickel has a closed shell in this condition. And they find systematic problems with the lines. So they are too narrow in the models compared to data for the three elements. But then there are differences which are not very well understood, because the windows seem to be present when you have an open shell, the case of chromium and iron, but they are not in nickel. So that is also something missing probably in the atomic models. But then there are some differences in the quasi-continuum that cannot be explained by, at least not in a naive way, by problems in atomic models. So there's still the possibility that this iron experiment had some flaw in its design. So the situation is uncertain. If one takes this result at face value, it would seem that models are underestimating the opacity by a substantial amount, as you can see here. So what can be done with neutrinos? Well, neutrinos, of course, you know, they come either from the PP chain or from the Cno cycle in the sun. They carry about 2% of the energy produced by the sun. The Cn is marginal in terms of the energetics, and this is very useful for us in the sun. It's only about 1% comes from CNO. Okay? And this gives us the possibility of using Cn fluxes to learn about the composition in the solar interior. If Cn would be dominant, this would not be possible. Okay. So this is the solar neutrino spectrum in general, and the latest results by Borexino are highlighted here from 2014-18, the PP detection and then measurement to about 10% uncertainty, and 2020, of course, the CNO detection. Okay. Now, before Borexino kicked in, the best results are here tabulated in the column solar. This comes from analysis of all solar neutrino data available at the time by Bergstrom and collaborators. These are the results here for precise determination of beryllium-7 and boron-8. On the side, you can see that later results by Borexino improved the beryllium-7 to 3% there. You can see the PP and PEP, which are very well determined when you use the luminosity constraint. Okay. When you don't, you can constrain this to about 10% or so. So it was 8% in Bergstrom a few years before it was to 15% for the PP and the PEP. So that was the situation more or less before Borexino. With Borexino, there was a direct measurement of PP, as we all know, to about 10%. Okay. there was now a measurement, not just upper limits, to the combined Cno flux, okay, of which, of course, nitrogen 13 and oxygen 15 are the dominant components. Okay. And putting Borexino results all together, and only Borexino, you get an estimate of the nuclear luminosity, as was shown in previous talks today, of the numbers. So it agrees with the solar luminosity of to 1% and with a 10% answer. So that's in very short terms the main result for Borexino in relation to solar.
You have 10 minutes.
Okay. Now, what can we learn from this? So let's go from PP to beryllium, boron, and then Cno, right? So PP is important because it completely dominates the energetics of the sun, which is summarized here in this equation, where the photon luminosity plus neutrino luminosity has to equal or to match the nuclear energy plus the gravothermal component, modulo the hypothetical existence of other energy source or sink in the sun, okay? So this is simply expressing here energy conservation. No. So if one can express the nuclear energy as a combination of the solar neutrino fluxes, then one has a measurement of the right-hand side of this equation, gravothermal energy, believing in the models, is tiny. So one can probably neglect it to first order. And so the idea of measuring a PP to very good precision, much better than what is currently available, would allow us to test to high precision the origin of the solar luminosity. If these equations don't match, then there should be some red sun here associated with some unknown energy channel, okay, which could be either a source or a sink, as mentioned before. This could be related to weak particles being lost from the sun, carrying energy to dark matter, annihilation, and so on and so forth. At the same time, there is these time scales that are different, because this comes here, the speed of light almost, so 8-minute time scale, whereas the radiation takes a lot of time to emerge from the sun. It was already mentioned earlier today. So one can also test in real time the dynamics of the sun eventually. And if it's a hydrostatic equilibrium, this should carry no difference, but if something is happening in the solar interior, we should be able to find a mismatch between these two sides of the equation. Okay. So that's a most important issue related to PP. Now to boron 8 and beryllium 7, one can try to relate it again to the composition problem. Now this nicely illustrates the behavior of the high metallicity and low metallicity models in a plane where you have boron 7 on the y-axis, boron 8 on the y-axis, beryllium 7 on the x-axis. And what you see here is how these two fluxes would react if one would change the central temperature of the sun. And you see clearly that changing the metallicity eventually amounts to changing the central temperature of the sun. Okay. So there's really no information in the composition in these two fluxes, but there is information on the temperature. And when you include all the uncertainties in the models that are related to changes in the model that would affect the temperature here, you can see that these are very well aligned here. Okay. When you include also the uncertainties related to nuclear reactions, of course, you get larger dispersion. Bottom line here is that first, the experimental result in the cross would agree with both models equally well, or almost equally well. The other thing to keep in mind, again, is that this would be only a measurement of the central temperature. So you can point towards high metallicity or low metallicity models, but in reality, what you would be pointing at is a hotter model or a cooler model. And you don't know with these fluxes how you get this hotter or cooler temperatures. It could be composition, it could be, for example, opacities. So this is always something to keep in mind. And there is where the Cno neutrinos play the major role, because Cno neutrinos will give you an extra dependence on the composition, which is independent on the opacity. And this would help us break this degeneracy. Okay, particularly the Cn part here. Okay. So these are the abundance profiles here. Okay, keep in mind, there's no net production of C plus N plus O, so that sum is constant in the sun, because Cno only catalyzes. Okay, And in particular, the Cn is almost constant because the NO part plays a very minor role. Okay. Now, you can relate changes in these Cn fluxes to changes in the Cn abundance of the solar core, to the changes in the temperatures there, and plus some contribution from the dominant nuclear reaction, which is nitrogen 14 plus proton here. Okay, the coefficients beta here basically reflect the temperature dependence of the fluxes with respect to temperature in the conditions at the solar center. Okay. Now, in the case of Borexino, we have a combination of these two fluxes, which is given by this equation here. So about 3/4 come from oxygen and 1/4 from nitrogen 13. So Borexino is actually measuring this combination. And this can be related the same way to the central temperature, but the central temperature itself can be eliminated from this equation if one has a reliable measurement of boron A, which is extremely sensitive to temperature as well. So after you do a little bit of algebra, you get to this sort of equation where this is something well constrained from experiments. And therefore, given a measurement here of the CNO flux, one could extract almost directly the composition of the solar core in terms of carbon nitrogen relative to a reference model, which only plays the role of reference. So in the end, it doesn't really matter. If you want to apply this to extract some constraints, for discrimination between the high and low metallicity, keep in mind that the difference in these fluxes, here expressed for oxygen, is about 40% between the low and high metallicity. So that gives you a feeling of the type of precision the measurement would require. If you want to go beyond the solar abundance problem and you want to study solar physics in a more general context, for example, the mixing processes that alter the composition of the sun during its evolution, you can take a look at the abundance of Cn in the core and in the surface. In the solar model today, this difference is about 15%. So that again gives you a feeling that you need a measurement of around 10% to start to open the possibility of getting some idea about the mixing processes in the sun. This is of course important because the same processes would apply to every other star, right? So ideally, this is a very important measurement to achieve. Okay. Now we have the CNO measurement by Borexino. We had the previous talk on the topic. The result is summarized here. This, in fact, this combination that was shown in the previous slide, 70%, 75% from oxygen, 25% from nitrogen. Okay. This, of course, is very nice in terms that it's really a detection of Cn, at least to a 5 sigma result. Okay. And now going back to the models, and here is a comparison between the fluxes, the neutrino fluxes from Bergstrom 2016, and then with the Borexino flux in particular. This is taken from a very nice paper by Salmon and collaborators. And let me highlight the last part here that you see in the ellipse, where you have the Borexino result for CNO and the location of different solar models according to the composition. Of course, the Cn at the moment, let's say, favors a little bit the high metallicity, but the errors are still too large to give a quantitative assessment between the high and low metallicity. Okay. If the central value...
5 minutes only.
Okay, I'm almost...
No, really 3 minutes, sorry, only 3 minutes.
That's okay, enough. If the central value of Borexino will remain as the errors go down, that would be, of course, a very nice, a very interesting result, because, of course, you can see here that not even the high metallicity model does not really match the central value. Of course, if one shrinks the errors by a lot, right? But it would be interesting if one can get eventually to 10%, because 10% is the same type of uncertainty you get from spectroscopic measurement. So you will be at the same level of spectroscopy, but for the abundance in the core. Okay. That's very nice. And so almost finishing, so future perspectives, okay, this is a list of experiments that could or would do solar neutrino measurements. This is taken from a paper that will come later this year by Ore Vigan. And this is trying to summarize the situation here, you see in green the Borexino results. Sorry. In red, the high metallicity, in yellow, the low metallicity, and the potential that the different experiments have here shown with the error bars. Right? So, okay, it's a very difficult measurement to achieve, but okay, at least in the mid-long-term future, the possibilities seem very interesting, especially when you get here, and you would really have a discrimination power between the different models with this experiment. Right? And let me emphasize again, these results could go well beyond the importance of the solar abundance problem, because then we would be able to start testing stellar physics phenomena, which affect all stars we observe in the sky. And on observations that all studies done now in galactic structure, galactic evolution, populations, etc., depend, because the stellar models depend crucially on our understanding of all these processes, and this is what gives us ages for the populations. And so it's really, really fundamental thing that one can see that this goes well beyond the absolute abundances or not, okay? And okay, finally, let me mention that there is another possibility with the Cno neutrino, which is related to the electron capture, right? So this is monochromatic signal. So potentially it's an interesting possibility, but of course the signal is very small. So it will require very large detectors. Okay. So to finish, I think, yeah, in fact, solar neutrino physics is entering or has entered precision era, which is very nice. And we can already start using this to learn about the solar core. This has been a very long way dating back maybe 50 years. Okay. And eventually we can continue, hopefully, on this line for the next 10, 15 years. Okay. We need to improve the solar models, that's clear. Okay. Particular work is being done on radiative opacities and nuclear cross-sections, which is very important. But we still keep some unresolved paths. Okay. And this goes again beyond the standard solar model paradigm. If you work within solar models in general and you introduce non-standard physical properties or processes, we still more or less come out with the same result, that low metallicity does not produce good helioseismology. And so far, there's not even a non-standard solution to this problem. So this keeps open. And with this, I finish. Thank you.
Thank you, Aldo. Do you have some question for him?
Gemma, I have a question regarding the first last slide, where you show the predictions. This one, yes, thank you. Predictions about CNO measurement from other experiments. I don't know if you collaborated in this work, but in any case, what are the assumptions behind Cno Plus and Juno in particular? Which
oh, okay, Aldo, I'm very sorry. I have to pass on your question, but I will find the answer for that to you later. Because
no, okay, thank you. No,
yeah,
no, I thought maybe you were.
I will tell Gabriel to.
No, the picture is clear. Just
sure. What is it? But she made this picture, so I will ask how she, where she took the numbers, let's say, to put it together. So, okay. But I'm very sorry. Very sorry.
Okay, thank you for the first two beans because.
Yeah, I understand. Yes. Sorry.
Okay, if you do not have additional comments or questions, we move to the Aldo Ianni talk.
Thank you.
About overall of a Cno cycle in massive stars.
So I share my screen. Can you see my screen?
Yes, you see your slides.
Okay.
Fine. They are also moving.
Okay, so good morning. I'm giving some presenting to you some considerations about this title, although some of the important discussion were already introduced by previous speakers. So without being too long, you know that this is the fundamental paradigm for energy production through hydrogen burning in stars, which go through two mechanisms, the PP chain and the Cno cycle. So I will make a few considerations about implications of the Cno cycle. So the PP cycle was discussed in this meeting. I want to underline that the PP cycle is the primary mechanism, in particular in first generation stars, where you have only hydrogen, so not heavy elements inside already produced by second and third generation stars. But a different mechanism could be in place for second and third generation stars, where you have already some amount of heavy elements inside the core. So this idea was independently introduced by von Weizsäcker and Bethe between 1937 and 39. Where they understood that the carbon, and together with carbon also other light elements such as nitrogen, could have played a role in burning hydrogen inside the stars. And this was studied in detail, and as a matter of fact, they proposed what has been already discussed by Aldo Serenelli, the Cn cycle, which can burn hydrogen similarly to the PP chain, and producing the same amount of energy, as a matter of fact. So this is the cycle where you have a P gamma. You can start, for example, but you can start from carbon, but also from nitrogen. You can start from carbon already present in the core at some extent, and with a P gamma interaction produce nitrogen, which then decays to make the electron neutrino, and then you have other P gamma interactions. Then at some point, you can end this cycle through a P alpha interaction, which again produce carbon, which works as a catalyst in this mechanism. So carbon is not consumed in this process, but only hydrogen is consumed. But also, and this is the standard most likely process in light stars as our sun, and produces energy cycling on the carbon and nitrogen and oxygen. But as you can see here, the P alpha interaction could also, we can have at this point the possibility of a low probability branch through a P gamma interaction. And this low probability branch will destroy, if you want, will not reproduce the carbon, which is feeding the interaction processes. So the relative probability of these two processes, P alpha and P gamma, depends on a number of factors, and also depends also on the interaction strength, which is on one case a nuclear interaction, and the other case an electromagnetic interaction. And you can also understand that with respect to the PP chain, here the the efficiency of this process increases with increasing energy, because the Coulomb barrier is higher in these interactions with respect to the interaction for the PP chain. As a matter of fact, if you look at the Coulomb barrier for the PP interaction, regardless the coupling strength, one can understand that and appreciate that the Coulomb barrier for the carbon P gamma interaction is much higher. So the probability at the same temperature is lower, and is with the P gamma on nitrogen 14 is even higher. And as a matter of fact, the capture on nitrogen 14 is the slowest process in the CN chain. But till 1950, it was considered the CN cycle the primary energy source in the sun. And for this reason, a number of measurements in order to understand the interaction rates, measurement on cross sections were carried out. And eventually it was understood that the CN cycle cannot be the dominant energy production in the sun, but it should be the PP chain for the sun, considering the solar mass and the temperature at the core. So this, as a matter of fact, is what we have understood today. But behind this mechanism, there is all the process concerning stellar interaction rates, which is an important physics aspect, also to understand how the CN cycle develops in larger stars, where the temperature in the core increases and also the abundance of element changes. However, to determine these interaction rates, one needs to measure the cross-section below 100 keV, which is a difficult task. And in most of the cases, this depends on extrapolation of high energy measurements. And this extrapolation can be even more difficult in case of resonances at high energy with big tail that extend to the sub 100 keV region. And this, as a matter of fact, is the case for a number of interaction processes in the CN and CNO cycle. Okay, but also using these interaction cross sections, one can also understand and determine the time scale of different processes inside the sun. So in any case, the solar standard model, as was discussed by Aldo Serenelli previously, gives a satisfactory account of what we know about the sun. And in particular, according to the standard model, regardless the metallicity, the prediction is that the Cno cycle should account for about 1% of the energy production. And this is, as a matter of fact, it has been proved by Borexino measurement, and it's a big achievement taking into account the complexity of the Cno cycle. And the complexity also that could help, as Aldo said and pointed out, to understand the physics in more massive stars. So coming back to the CN cycle, as I said, there is a branch, and this branch is on capture on nitrogen 15, which could reproduce to a P alpha interaction carbon, or branch out to a different sequence of interaction processes producing oxygen. And when you produce oxygen, then you produce later fluor 17, and then you can produce even heavier elements such as fluor 18. So in this branch, the probability of this branch depends on the effective cross-section ratio for the P alpha and P gamma processes. And one can determine that the P alpha process has a cross section which is and a relative probability which is something like 2,000 times more than the P gamma process. So the P gamma process is a low probability branch at the solar temperature, and does not introduce any further input in the energy production, but it's also, so it's negligible from this point of view, but it's important for the nucleosynthesis of heavy elements, in this case in particular oxygen 16 and oxygen 17 and fluor. This is the second branch, and as was pointed out earlier, this second branch develops the Cno bicycle, and this double cycle develops as highlighted in this slide. And on the left, you can see the main cycle, which is the Cn cycle, also referred to as the cold Cno cycle, because works at low temperature, the temperature of the inside the core of the sun, or in slighter, more massive stars. And then the other cycle, which, as I said, it's important also in terms of nucleosynthesis for the solar physics. However, in more extreme environments, even outside the main sequence behavior of stars, one can have a more complex behavior, which is highlighted in this slide. So the beta decay of nitrogen 13 could be at some point slower than the P gamma interaction, which produces oxygen 14, which then decay beta to nitrogen 14, and then there is a coupling back to the Cn cycle. So this more complex behavior of the Cno cycle can develop in extreme environments where the temperature is much, the core temperature much larger than in the sun, and in stars outside the main sequence population. So the same can happen for the second branch of the Cno cycle, where the fluor can produce a neon 18 and then start another cycle. So this there are the branches that couples together in these extreme environments and make more complicated the so-called standard Cno bicycle. So as we have said, and also said by heard from previous speakers, the case of the sun, it's a particular one, because the temperature is, the mass and the temperature is such that the PP chain is dominant, although the temperature dependence of the energy production in the PP chain is much smaller than in the Cno cycle. As you can see, the temperature dependent, it's very strong for the Cno cycle. Also, this depends on the Coulomb barriers, which is larger for the interaction processes involved in the Cno cycle. However, when you go above 1.3, something like that, solar masses, the Cno cycle becomes more important, more and more important. And eventually, if you imagine to go to the an extreme case, the ratio of the to energy production will be proportional to the ratio of the interaction, the strength of the interaction processes between the nuclear process involved in the Cno cycle and the electroweak process involved, nuclear electromagnetic process involved in the Cno cycle in particular, and the electroweak process involved in the PP cycle. So this slide...
7 minutes to the end, Aldo.
Sorry, Gemma?
7 minutes to the
7
end.
minutes, okay. So this slide has been discussed, so I'm not going to the detail. This is the measurement performed by Borexino, where one can appreciate the accuracy for the beryllium-7 and boro-8 in particular. And if one takes into account also that considering Super Kamiokande and Cno, the accuracy on the boro-8 goes down to 3%. So one can think that maybe the solar metallicity problem, as was highlighted by Aldo Serenelli, can be solved looking at the beryllium and boro-8 neutrinos, but this is not the case, and this has been discussed by Aldo Serenelli. Is not enough. So you need some additional contribution from the, in particular from the Cno neutrinos. So what on the contrary, it's important to highlight is the fact that already using the solar neutrino measurement from Cno by Borexino, in spite of the low accuracy of the present result, one can measure the solar luminosity in terms of Cno neutrinos only, which is consistent, although with a large error at the present time, with the prediction of solar standard model. So in my opinion, this is already an important achievement, taking into account that the Cno, it's a tiny fraction of the energy production in the sun due to the low temperature in the core. So additional cycles. A Cno cycle can develop in a more complicated set of interaction processes. As a matter of fact, the p alpha interaction on the proton capture on oxygen can branch to a p alpha or p gamma interaction. So one has to take into account the probability of these two interactions, and it turns out that if one study the interaction rate for the capture on oxygen 17, there is a range of temperatures where these interactions, the ratio of the interactions, it's almost equal to 1. So then at that point, the production of fluor 18 is not longer negligible. And so one has to take into account in this environment, which is not the case, is not for the sun, but it's a different environment, the possibility to produce fluor 18 and then develop a different sequence of interactions, which produces oxygen 18 and then eventually recouple to the previous cycle. So this means that in a specific environment, the Cno cycle is no longer bicycle, but can tricycle. And this is highlighted in this slide, where you see that at some point, the oxygen 18 can branch to produce a p alpha interaction or a p gamma interaction. So the p alpha interaction goes back to nitrogen 15, producing the third cycle in the Cno energy production. Actually, this is a hydrogen burning involving carbon and nitrogen and oxygen. But there is also the possibility that you produce fluor 19. And so there is also a possibility of a fourth cycle. And as a matter of fact, there is a fourth cycle contemplated. And this fourth cycle, again, studying the relative probability of interaction processes, can be important in environments where you have a very high temperature. So in specifically in above 10 to the 9 Kelvin, then the probability of having a fourth cycle is no longer negligible, and although at the level of 1%, but you can develop another cycle where you are of this kind, where you have involved oxygen 16 to fluor 18 and fluor 19. So this fluor-19 then can also produce through a P gamma interaction neon. So at that point, if you produce neon, there is no longer a back process which couples into the previous cycles. And then eventually the Cno catalytic cycle will stop, giving rise to a so-called neon sodium cycle in the energy production of very massive stars. So, but in any case, these coupled cycles are important for nucleosynthesis of heavier elements in star environments. So, a further consideration about how important is the Cno cycle in energy production for main sequence stars. So if one looks at the luminosity-mass relationship, one can see that there is a power law which also determines the lifetime of stars. And this power law, which is the luminosity is proportional to m to the 3.5, works on a very wide range of star masses. As a matter of fact, if one zoom in the different mass regions, then the behavior is a little bit different. And for example, between 1 and 10 solar masses, the power law is closer to m to the 4 than m to the 3.5. But on a wider range, the power, it's closer to 3.5. So one can use this information coupled to the star number density, which decreases as a power law m to the minus 2.5, to understand or to try to quantify the amount of energy produced by Cno cycle. So we know that above 1.3 solar masses, the Cno cycle is dominant. Although the density of stars, the number density is decreasing, and stars are dying faster because are burning the core much faster. So a 10 solar mass star will, as a time scale of 1,000 times less than a solar mass star. So this star number density behavior tells us that 90% of stars presently shining will end up in white dwarf. So they are small mass because stars ending up in white dwarf, they have to have a mass smaller than the Chandrasekhar limit. So doing this,
the time is over.
See, doing this small exercise, the ratio of energy production in stars dominated the PP chain with respect to the ratio of energy production of stars dominated by Cno cycle, it's smaller than 1, quite smaller than 1, implying that the most of the energy shining is produced by the Cno cycle. So in conclusion, the Cno bicycle is a crucial mechanism in stars, in particular in low mass stars. The Cno cycle is dominated by the so-called Cn cold cycle, but this cycle can develop in more complicated processes in a third and fourth Cno cycle in higher mass stars or in stars which are leaving the main sequence population. So this is all. Thank you for your attention.
Thank you, Aldo, for your very interesting talk. Do you have a question?
I do, if
Please.
possible, very short. Yeah. Aldo, have you seen or done some even approximate calculations as to the overall contribution of Cno versus PP at the galactic level? So in
at the galactic level.
Yeah.
Well, maybe you are more inside this, but this picture, I think, should work also at galactic level as an order of magnitude. Then maybe different galaxies have a different population of stars, but I think on average this fact that 90% of stars previously produced or at present shining are small in mass. This is, I think, it's a general result.
Okay.
So this picture should be valid because I understand that this 90% parameter is a general agreed number for previous formed stars and present stars. As far as I can tell. But,
Okay. Okay, thank you.
It's time to move to the last talk of the session.
Okay, thank you. I stop sharing.
Thanks, Aldo. Thanks, everybody. So the last talk is about antineutrinos detection in Borexino. So it's slightly different subject and from Sandra Zavatarelli.
Okay, I try to share my screen. Okay, share the desktop. Oops, is it working?
We see.
Yes. So, sorry, because I have some overlap of windows. Okay, do you see it?
Yes.
Okay. Tell me if it moves or not. Is it moving?
It's moving.
Okay, fine, it works. So, okay, in my talk, I will present the Borexino studies about antineutrinos coming from the cosmos and from the Earth. In particular, I will start by describing the large variety of sources of antineutrinos and how we can detect them with liquid scintillator. Then I will present some of the Borexino results about, in particular, neutrinos, the diffuse supernova neutrino background, and the possible signal time correlated with gamma ray bursts and solar flares. And I will conclude with the perspectives. Now, the astrophysical neutrino, as you can see from this picture, cover at least 18 order of magnitude in energy, starting from milli-electron-volt up to penta-electron-volt. And electron antineutrinos been emitted during the BBN by the neutron and tritium decay, and are continuously emitted by our planet in the decay of the uranium, thorium, and potassium isotopes that are embedded in the rocks of the crust and of the mantle. Moving to higher energy, we find the reactor antineutrinos that are emitted by the decay of the uranium and plutonium fission fragments. While we have several mixed sources of both neutrinos and antineutrinos that are the relic neutrinos. And moving to higher energy, we found the solar thermal neutrinos, where you can see from this panel, the Brestral, Compton, and plasmon decay emits an equal amount of antineutrino and neutrinos. Moving to higher energy, we found the diffuse supernova neutrino background, the atmospheric neutrinos, and at very, very high energy, we have galactic and extragalactic possible sources, such as the gamma ray burst, the active galactic nuclei, and the star-forming galaxies. Now, in the energy range of interest for the Borexino study, the antineutrinos can be detected to main channels. The first one is the elastic scattering process, but has no threshold, and this is sensitive to all the neutrino flavors. In particular, the cross-section for neutrinos are on average a factor 5-6 higher respect to the muonic and tauonic flavor because of the contribution of the charged current interaction terms. Here in this panel, you can see the cross-section for the electron neutrinos, and is compared in red with the cross-section of electron antineutrinos. But for this last particle, we have a very interesting and promising channel, which is represented by the inverse beta decay process that, as you can see, I highlighted in blue, has a cross-section which is a factor 100 higher respect to the elastic scattering. In the inverse beta decay, electron antineutrino interact with the proton, giving a positron and a neutron. The positron immediately annihilate, giving a prompt signal, and then the neutron thermalize. And after a time that for the Borexino experiment is of the order of 250 microseconds, it is captured by a proton or by a carbon atoms, giving a characteristic capture gamma ray. And so the coincidence between the prompt and the delayed event is a very clean signature for the occurrence of this process, and so of electron antineutrino interaction. Another important feature is that the energy of the prompt event is strictly correlated, you see very simply an energy offset, to the energy of the incoming antineutrino. Therefore, we can precisely reconstruct the energy of the electron antineutrino that gave the interaction. The only drawback is that there is an energy threshold and it is equal to 1.8 megaelectron volt. So you have already heard about the performance of the Borexino detector. I want just to recall that we have two main diaco systems. The primary one that is called LABEN, that has been developed for the solar neutrino physics, and so it provides good linearity, but only up to few MeV, especially for events far from the center. And for higher energy, up to 50 megaelectron volt, we have developed an independent system based on 4096 pathway from digitizer named Flash ADC system. And each of these digitizer reads the sum up to 24 photomultipliers. So for the study of antineutrinos from astrophysical sources, we have combined both the systems. So let me start from the first result about the neutrinos. Well, it is known from measurement that our planet is emitted an amount of heat equal to 47 terawatt plus minus 2. This has been determined by measuring the temperature gradient along more than 10 to 4 boreholes spread all around the world and integrating these numbers with geological models. And the point is, where is all this energy coming from? In principle, there are two main possible sources. One is the secular cooling, and another is are the radioactive decays. In fact, in the crust and in the mantle are embedded uranium and thorium and potassium isotopes whose decays could, of course, emit also some fixed amount of heat. And in general, it is not at all known the relative amount of this contribution. For example, if we consider just one category of possible geological models that are these bar silicator models, these are models that describe the composition of the Earth immediately after the core differentiation. And if you look to this table, you can see that among different models still of the same category, there are differences larger as a factor 3 between, you see, the cosmochemical and the geophysical models, that becomes a factor 10 for what concerns the prediction about the total radiogenic heat. And the reason for the difference among these models is, in practice, the choice of the meteorite that has been chosen as representative of the primeval solar nebular composition. The cosmochemical models are based on the statine chondrites, the geochemical on the carbonaceous chondrites, while the geophysical models also consider the amount of heat that has been, as it is necessary to support the mantle convection. And this in particular, this last category is the one that foresee the highest amount of radiogenic heat. And so you can understand that the overall picture is indeed really unclear. But in the case of the thorium, uranium, and potassium isotopes are emitted antineutrinos. So in principle, if you are able to precisely measure these neutrino fluxes, we can determine it producing element abundances, because there is a fixed relation between the antineutrino flux and the abundances of the isotopes, and this relation is provided by the nuclear physics laws. And from is producing element abundances, we can understand the Earth energetics, and in particular the importance of the radiogenic heat. In order to study the neutrino fluxes, it is important to perform multi-site measurement, because in general the flux from the crust but also from the mantle could be not homogeneous. Since in general the number of events expected is not so large, a very, let's say, promising channel to detect this particle is represented by the inverse beta decay process. And in particular, here in the panel on the left are shown the neutrino energy spectra. Since this process has a threshold at 1.8 MeV, you can see that only uranium-238 and thorium are able to produce enough energetic neutrinos able to overcome this threshold. And if one considers the energy dependence on the inverse beta decay process, on the right, you can see which is the expected spectrum for the neutrino in a liquid scintillator. And you can see in particular that the thorium and uranium neutrinos show a different endpoint. So by making a spectral analysis of the detected event, is also possible to distinguish these two contributions. Now we could ask which is the expected signal, in particular at Gran Sasso, which is the site of the Borexino experiment. And it is very important to determine the contribution coming from the local geology, from the rocks that are closer to the detector, because as you can see, it is expected that 40% of the signal comes from an area of 500 kilometers around the detector site. And so precise directly rock studies have been performed in the area around the Gran Sasso, you see in this region, which is a square of a side of 400 kilometers. And from this direct rock sampling and geological three-dimensional models has been determined that the contribution due to this part here highlighted in green, the so-called local crust, amounts to 9.2 TNU. What are TNU? TNU, it is a particular unit adopted in this field named terrestrial neutrino units that corresponds to one event detected over 10 to 32 target protons in 1 year. And this is an amount of protons that correspond more or less to 1 kiloton mass liquid scintillator. So it is particularly useful for this kind of detector and studies this unit. And so the contribution coming from the local crust is relatively well known, and the same is true for what is called the far-field lithosphere, that is the sum of the crust and of the uppermost part of the mantle. And because, I mean, these layers can be directly studied, also taking some rock samples. And so the amount of the far-field lithosphere is estimated to 16.7 TNU. And so the whole contribution, the sum of the two, is named bulk lithosphere, and it contributes in the Boraxino detector to 25.9 TNU with 20% error. While on the other side, the contribution coming from the mantle is not at all known. As you can see, indeed, there is more than a factor 10 uncertainty depending on the choice of the Earth model. And indeed, this is the contribution that we have to determine through our studies. The neutrino signal has been already detected by the Borexino and the Camland experiment with very high statistical significance. I quoted here the most updated result. We have also heard yesterday the description about the result of Camland in the talk about by Tatsuo. And so I refer for the details about the neutrino analysis to its talk. And in the following, I will detail the last result from Borexino. You can find here the reference paper. We analyzed the statistics up to April 2019, and you can find the details of the analysis cut. The relevant improvement respect our previous analysis done in 2015 are, let's say, an improved cosmogenic cut, because now we lose only 2.2% of the exposure, while with the previous cut we were losing 10%, so we have performed a strong improvement. And also for this analysis we have adopted a large fiducial volume. We are asking that the prompt event, is constructed at a distance larger than 10 centimeters from the vessel, while in the previous analysis it was 25. So we also enlarged the fiducial volume. And okay, in this statistical sample, we detected 154 events that surpassed our selecting cuts. And as you can see here, here is shown the charge of the prompt event, and here on the right of the delayed event. And you can recognize the capture peak of the neutron on protons and on carbon atoms. In this panel, it is shown the prompt distance from the inner vessel, and as you can see, it follows pretty well what it is expected from our Monte Carlo. This is important because it highlights that there is no excess at a large distance. That means a possible presence of external backgrounds. And for what concerns the background, indeed, we had to develop a very detailed study. The most important background for the geoneutrino study is represented by the reactor antineutrinos. And there are 440 reactors spread all over the world. And in particular, we are in contact with the International Atomic Agency that provides us on a monthly basis the thermal powers produced by each single plant. And so we developed a code that is able to compute with high precision, also taking into account the neutrino oscillation. We are able to predict the code at Gran Sasso. And presently, the most important source of uncertainty is represented by the spectra at emission, because there are reference spectra from Muller et al. In 2011, but the reactor antineutrino experiments such as Diabei, Reno, and Double Show put in evidence fluxes that on average are smaller and also show a different shape in the energy region around 5 MeV. In order to understand the impact on our result of this uncertainty, we have computed the number of expected events in our statistical sample, considering both the shapes, the one from Muller and the one measured by the Diabei experiment. And so, as you can see, in the case of the Muller spectra, we expect 97.6 events in our sample, while considering the normalization to Diabei, we get 91.9. So there is a 6% difference that we have included in our systematical uncertainty budget. Another important source of background, even much smaller respect to the previous one, is represented by the atmospheric neutrinos that may give both charged current and neutral current interaction with the atoms, mainly carbon and hydrogen, that constitute the Borexino scintillator. And besides the inverse beta decay, they also can give several other reactions that could mimic the inverse beta decay interaction. And so we have developed the simulation considering the ondal fluxes for energies above 100 MeV and the Flucal one that are more precise below 100 MeV. We have also included the matter effect and simulated the detector response and applied the same selection cut as for real data. And in the present sample, we estimate that 9.2 events are due to atmospheric neutrino. You can see here on the right the expected charge spectrum after the inverse beta decay selection cut for the prompt event. Then there are also non-antineutrino background, but we evaluate each contribution in detail. But let me say that the sum of this background indeed amount to a number of events that indeed is really small. It is a factor 10 smaller, for example, respect to the background coming from reactor antineutrinos. So we included, of course, in the analysis, but this is, let's say, a less important contribution. The most important contribution is coming from accidental coincidences that, for example, we have estimated from an off-time coincidence windows. We choose these events with a difference in time between the prompt and the delay in the energy, in the time range between 2 and 20 seconds, while the correlation times, as I told before, is 250 microseconds. So in order to determine the number of geoneutrino events that is present in our sample of 154 candidates, we have performed the spectral fit of the prompt event. And in particular, in this fit, we have fixed all the not antineutrino background and the atmospheric one to what are the expectations, as I showed in the previous slide, while we left the contribution from the reactor antineutrinos completely unconstrained. For what concerns the signal coming from geoneutrino, we made, let's say, to attempt. First, we fixed the ratio between the thorium and uranium signal to what it is expected according to the measurement of the chondritic meteorites. But this ratio is 2.7, while in the case we have also repeated this fit, leaving these two contributions free. And we got perfectly consistent results. So here I quoted the result obtained with the ratio fixed. And in particular, our fit gave a number of geoneutrino events equal to 52.6. that corresponds to 47 TNU. And so you see that the achieved precision is equal to 18%. And here in this plot, it is shown, the number of geoneutrino event that the fit return as a function of the number of reactor event. And you can see that the comparison between the result of the fit fixing the chondritic ratio to one demonstrated by the meteorites, or leaving the ratio between the two contribution fit, and you can see we get perfectly consistent result at these two dots. And the other important point is that the number of events that we get from the fit is perfectly compatible to the one predicted on the base of the dedicated code about the reactor antineutrinos. So as you can see, this in particular, the dashed line is the result obtained by considering the spectrum normalized to diabae, and the continuous line represented the one without the excess. And as you can see, also this one is perfectly compatible with the results of our fit. So the overall picture is really consistent. And among the source of systematic uncertainty, you can see that the shape of the reactor spectrum and the atmospheric neutrino did contribute for a negligible fraction to the overall budget. And the most important contribution is coming from the precision of the position reconstruction algorithm. But as I explained in the introduction, the real goal of our study is to try to understand which is the signal from the mantle. And in order to get this contribution, we have introduced in the fit a further component, which is the expected signal from the bulk lithosphere. As I explained before, this is known from a direct rock sampling and three-dimensional model, and we know that this contribution amount in our present statistic to 28.8 plus minus 5.6 events. So we have introduced in the fit this component, leaving, of course, free to let's say, to change within the error, and with a ratio of uranium and thorium, which is the one that is typical of the lithosphere, that it is 0.29, not the same as, let's say, for the whole sum of the crust and mantle. And by performing this fit, we have got a signal from the mantle that corresponds to 21.2 TNU, that 23.7 events that are 21.2 TNU, sorry, because I want to say this result both in terms of event that TNU for clarity. And so this is the flux, and making, studying with Toy Monte Carlo the distribution of making a sensitivity study, we have demonstrated that we have an evidence at 99% we can exclude the null hypothesis of a mantle signal. And here you can find instead on the right a comparison between our results and the prediction from the geological models. And you can see that our median signal is much more in agreement with the expectation from the geodynamical model, And, but of course, still the error bars is quite large. An important point is to try to translate this signal into a radiogenic heat from the mantle. And to perform this let's say, calculation, we need also to understand how they can be distributed, the uranium and thorium, because of course we don't know, we register the overall signal. And so to make, let's say, this calculation, we have made two extreme hypotheses. The first one is lighted here red. This curve corresponds to assume that uranium and thorium are homogeneously distributed. And the second one, this low curve in blue, corresponds to the assumption that all uranium and thorium are displaced closer to the mantle and core boundary. Of course, this is the assumption that predict the largest distance from the surface and the detector, so it gives the lowest signal. And so we think that the reality is something in between. So, okay, considering the trend of these two curves, we estimated the contribution from the mantle radiogenic heat equal to 24.6 terawatt. Okay, you can see this here.
Sandra, we are running a little bit out of time. And I
Sorry.
fear that the connection will be cut.
How much time?
You are already 3 minutes over your time.
Okay, so sorry, just I can conclude with this slide, just saying that we also tried to, I'm sorry, I also, that we also tried to, let's say, to compute which, I mean, the expectation for the total radiogenic heat that is coherent with our measurement. And of course, for making this comparison, we need also to consider the contribution from the potassium-40. And we assumed that the contribution for potassium-40 is equal to 18%. Because, I mean, this is what it is expected from the isotopical, the chemical abundance is observed in the meteorites. And so our measured signal corresponds to 38.2 terawatt of total radiogenic heat. And as you can see, comparing our result to what it is obtained from the other Earth models, in particular the several, you can find here the list, and you can see that our result is more close to what is expected according to the Turcotte and Schubert model, which is a geodynamical model. And so Borexino estimate a high probability at the level of 85% that the radiative decay produce more than half of the total Earth heat. And this is okay. I can conclude here with this slide. Thanks.
Thanks a lot, Sandra. Do you have a question? Okay. So if not, I think we can close the session here. And I would like to thank a lot to all the speakers. And there will be the last appointment tomorrow for another parallel session of this type. Thanks a lot to everybody. Bye.
Thank you.
Bye.
Bye-bye.